were to fall into a black hole, or as we say in academic circles, if we were to send a graduate student into a black hole, right? The person, if they went into a small black hole, would get ripped apart in a violent explosion, right? But if it was a large one, they'd actually see what happened to them. They'd be going in there. We'd see them waving to us, right? We'd standing outside the black hole. We'd see them waving, and they wave slower and slower, right? If they were wearing a blue shirt, the blue shirt would look more and more red as they went in, and then they would wave slower and slower. Eventually, they would stop waving, and they would fade from vision. Kind of this reddish, dull image of them would fade from sight as the last of the photons sort of got to you, and then they'd be gone. They, however, would just go on in there and experience whatever it is that's on the other side of that, right? Spaceships could go through large ones. So just remember that. Don't go through the small black holes. It's a little tough. It's a little tough on the stuff you're made out of, right? Try this one. Just try this on your whiteboards. If your neighbor is asleep, wake them up gently and tell them it's time to do whiteboard problems. Yeah, just do it on a whiteboard. Whiteboard.
Oh, look at this artwork.
Slug bug. Nobody's taking advantage of this. I'm trying to get people to hit each other. Where slug bug might escalate to slap bug. Trash talk bug. This is not meant to be a factual statement. Yeah. Do you know that Glenn Beck was caught killing kittens in his house?
What?
And selling the videos?
Wow.
That was not meant to be a factual statement.
Hey, you can't do that, Murray.
Was I recording? Oh dear, I'm in trouble.
Murray, is it 1.43 of the 26?
That was not meant to be a factual statement. Let me just. Didn't you guys hear that? There was some guy. He said 90% of what Planned Parenthood does is that's right, is abortions. And then he said later, well, that wasn't meant to be a factual statement. That's right. Turns out not to be very close to truth. Unless you think 2% is close to 90%. That's right.
Have you read the other two of his dark materials?
Of his what?
Have you read the other?
Yes, we read them all. That's right. That's right. I think I was
The movie was a disappointment.
yeah, the kids read those, I think, to themselves. That's right. And I just read them because I couldn't get them to let me read them to them. That's right. I think. Or maybe, no, I think that might have been one of the last books we actually read together. That's right. Maybe we got through the first one and then, that's right. Yeah. You got it.
Oh, look at that koala. That's not cool. We shall call this land.
4.3 times 10 to the 33rd. Are we good? Has everybody been able to... so you're solving for mass, right? 6.38 times 10 to the... that. Yeah. Do you get it? I can't read that. 4.3 times 10 to the 33rd. Good job. That's what you got to do mathematically. Yeah, we're just using the Earth's size as just an arbitrary thing.
Look at that. And just imagine it would be terrible because it would never be as good as the
Yeah.
Since we were looking for the radius and the mass of it.
Yeah.
The last time we already had our Pretty much we use the mass of the sun.
That dog will hunt. Only it's kilograms. M's for mass. Or Mary. Yeah.
We're all flatlanders. That's a lane. I think it's from pre-con.
Bless you. Yeah. Yes.
The what they wanted us to read. Yeah, I remember that. Did I read it?
Say it again.
Should I?
Yeah, that about that. Yeah.
Considering my grade.
Boys and girls, class. Let's suppose that we are in the top one here, okay? And this ship is accelerating. And remember, anything, by the way, I explained with acceleration, gravity will also do the same thing, right? Okay. And I'm accelerating. This ship is accelerating that way. It's in deep space. Let's ignore gravity for now and just look at acceleration. If I'm up there and I'm looking at this clock, okay, one of the weird things is that gravitational fields and accelerations make clocks run slow. Okay? Clocks that are lower than us run slower than clocks that are above us, right? Okay? So low clocks run slow. A clock placed at the bottom of a skyscraper in a gravitational field will lag behind a clock at the top. Okay? Time itself slows down, not just the clock, but time itself. Cheese molds slower, right? What? No, on Earth we'll do that calculation. It's fairly small. Okay, but here's how it works. And Feynman, Richard Feynman, if you're going to go on in physics, have your parents buy you the Feynman lectures in physics, because he was this brilliant teacher, and his textbook is not so much that good a textbook for people that don't know it. But if you've already learned physics, you can go back and read it and go, oh, I never understood that. Now I do. So here's how he explains this. Suppose you're looking back at this clock. Let's suppose, for convenience sake, the clock is flashing. Okay. Now, when it flashes, because we're accelerating, I will have moved from this position and I will move some distance before this light gets to me, correct? Of course, I measure the light going the speed of light, so there's no great mystery there. It's always going the speed of light when observed. But the first time I do it, it actually takes a little bit longer than it might to see that flash. But the next time it flashes, aren't I going even faster because I'm accelerating? Won't I have even gone even farther the next time? So won't there be an even greater length of time between the last flash and this one? It'll be longer, won't it? Yeah? And then the next time I see it, I'll be going even faster and it'll be longer. Every time I see it, I'm going to see it taking a longer time than it would have taken had we not been accelerating, right? So therefore, when we look at this, we're always seeing those flashes. If they're supposed to be 1 second, I'm seeing them, if I'm accelerating fast enough, at 1.1 seconds. Isn't that a little bit crazy? I'm seeing them always 1.1 seconds. Now, of course, if you go backwards, it's like, no, it must be the time is actually traveling at a slower rate, okay, than it is up there, right? This is just a crazy thing. Everybody, you can hear like people going, I can hear machinery grinding in the back of your heads, right? Yeah. This is a difficult thing, right? And the same thing, by the way, works for this. We're always going to see them a bit faster than we would have had we not been accelerating. So we see the the high clock running fast, the low clock running slow.
So wouldn't that mean that it would eventually just stop?
Well, no, it's not that the rate is going slower. It's just that we see it slower. This is somewhat paradoxical, but yeah, right.
The speed of light and you're traveling.
No. If your acceleration increases, so let's say I have a particular acceleration, I always see it at 1.1 seconds, right? If I go to another acceleration, a greater one, I'll see it at 1.2 seconds between flashes, right? And if we accelerate not quite so much, it might be 1.05 seconds between flashes, right? So it's the rate of acceleration corresponds to a particular difference in time passage. This is a little bit crazy, right? And the explanation doesn't work that great for that. So anyway, blah, 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 yay. Okay, so basically if an acceleration can cause this, then so can a gravitational field. So some massive object will also cause clocks to run slow. Now, what's interesting is that you can explain this another one of two ways, right? When we look at light coming from quasars, if you recall, are like the Saturn-like rings, accretion disks around a black hole. They are outside the event horizon, or otherwise we couldn't see them, right? They're really bright. As matter falls in, 10% of that matter gets converted directly to energy in its final, like, death spiral into the black hole. Okay. Now, think about the radiation coming from the event horizon of a supergiant black hole. Okay. It is like that sheet of rubber that we talked about last year and we just talked about, right? It is like